Hello again, folks. So last time we talked about how to find the composition, how to find what an object's made out of, and we talked about this concept of an absorption spectrum or an emission spectrum. Both of them will allow us to, by looking at those individual lines, we can figure out what the object's made out of. So today we're going to show you something else we can do with those. And as I mentioned at the end of the lecture last time, sometimes those lines, when we observe them, the pattern is correct, but everything's shifted over. So what's happening though is that's the velocity, that's the Doppler effect. And if you've ever been pulled over by the cops, you don't have to admit it, you actually are very familiar with the Doppler effect because it's Doppler radar that they're using for checking your speed. So let's see if we can figure out how that works. All right, so we've talked about light as information and how we get the temperature and the size come out of the continuous spectrum. The composition then comes out of either the emission or the absorption spectrum. What we're going to talk about today is the velocity. And so what we're talking about is that emission or absorption spectrum, but then how much those lines shift. So remember that in an absorption spectrum, we've got to have this hot, dense, glowing object like the core of the star. That's producing the rainbow. Remember, a hot, dense, glowing object produces a rainbow. You need to know what produces these three types. Whenever that light shines through a cooler, lower density gas, like the atmosphere of the star, then that atmosphere is going to absorb some specific colors based on the atomic structure. And so that's what's producing these black lines here. So let's think about sound. Sound is also a wave, just like light. So what if you're standing by the side of the road and there's an ambulance coming towards you and you hear its siren, it's really high, right? But then after it passes, it's and so even if a car is passing, it's you like the sound effects? I worked really hard on these. From that. Well, what's making the sound higher pitched? It's got a higher frequency, which you know means it's got a shorter wavelength. So when the ambulance emits a sound wave, before it can emit the next one, it's actually caught up to it. And so the next one is closer, and so on and so on. So these waves here in front, because it's moving closer to it, it's got a shorter wavelength than the waves behind it. Well, you guys know short wavelength is higher frequency. So this is why it's a higher pitch. And by the way, this is also what we think about when we talk about the sound barrier. When the airplane is moving faster and faster and faster, sound is just air. It's just vibrating air molecules. So when it compresses these, when it's caught up to its sound, it's got this big wall of air right in front of it. When it finally goes faster than the speed of sound, it breaks through that wall, and behind it, the air smacks together, and that's what's producing the sonic boom that you hear. So when the ambulance or the airplane are coming towards you, then it's got a shorter wavelength, so it's going to have a higher frequency. It's going to sound higher. When it moves away from you, now I've got the opposite thing. The ambulance is leaving its sound waves behind. And so the wavelength here, the distance between the waves here, is actually longer than it normally would. And so what that means then is we're going to hear a lower frequency because it's got a longer wavelength. So that's the yoom as it goes by. When it's directly in front of us, if it's moving across, there's not going to be any shift at all, right? Because it's neither leaving behind or catching up. So just because I don't have a Doppler shift, just because I don't have this compression or stretching of the waves, doesn't mean that it's not moving. Don't get fooled. What it means is that it's neither moving towards me or away from me. It could be moving directly in front of me, then I'm not going to see it. So the only time you hear the actual sound of that car is when it's right in front of you. Now you're hearing the real, for that brief instant, you're hearing the actual sound of the car. All right, so the Doppler formula, this is how we calculate the velocity. Now, with police radar, for example, they know what wavelength of light, radio, they send out. They know the specific wavelength. So the radar gun sends out that pulse of radar light. It bounces back. But when it bounces off of your car, since you're moving away, the wavelength is going to get longer. It's going to be shifted if you're moving away from it. So the observed wavelength is going to be different from the rest wavelength, the wavelength that we sent out to begin with. So using this formula then, we can actually calculate what the actual velocity is. And so this is the wavelength of the observed, this is what I got back. This is the rest wavelength, that's what I sent out. So you subtract those two, divide by the rest wavelength, and then multiply by the speed of light. Now, what we use for the speed of light depends upon what units I want my answer in. And we'll talk about this in a minute, but 3 times 10 to the 8th meters per second if I want my velocity in meters per second, or 3 times 10 to the 5th kilometers per second if I want this in kilometers per second. Always read the units carefully. Again, we'll talk about that in a second. So there is a shorter way to write this. I could also talk about the shift in the wavelength. This delta symbol, this capital letter, Greek letter delta, means change in. So this is, whenever you see that, I want your brain to read that as change in wavelength. And that's what this is. It's the change in wavelength. So, you know, if I started out with a wavelength, if my rest wavelength was 656 nanometers, but I observed it at 657 nanometers, then my shift is just one nanometer. And a lot of times this is a lot faster to work with than figuring out what the observed and the rest is and subtracting them. It saves you a step. And hey, we're lazy, right? So let's see what happens with light when we're using the Doppler shift. So here's our comparison spectrum. We've got a red line, a teal line, and a purple line. So this is the rest spectrum. Blue shift means it's moving towards us. And we call it blue shift because it's going to be shifted to shorter wavelengths. And think about that. When it's moving towards us, the wavelength gets shorter and shorter and shorter, right? And you guys know that shorter wavelength is towards the blue end of the spectrum, so we call this a blue shift. And red shift then, of course, would be it's moving away because it's been shifted to longer wavelengths, because as the thing's moving away, it's stretching out those wavelengths, it's leaving them behind. So as the wavelength gets longer, we know that that's shifting towards the red end of the spectrum. So the amount of the shift, either from here to here or from here to here, tells you the velocity. So it's how much it's shifted that gives you the velocity. The direction of the shift, whether it's blue shifted or red shifted, tells you whether it's moving towards or away. So in this case, because the distance, if the distance from here to here were the same as the distance from here to here, they'd be moving at the same speed. It's just one would be coming towards us and one would be going away from us. All right, so let's take a quick quiz. I want you to pause the video when we finish here, but here's your rest spectrum. I want you to tell me which of these 3 stars is moving towards you. Pause the video and figure it out. Okay, hopefully you actually pause the video, because it doesn't do you any good if you don't actually do the exercise and think about it. So this is the blue end, this is the red end. If it's moving towards us, is it going to be blue shifted or red shifted? It's going to be blue shifted. So that means that the line should be shifted towards the blue. Well, here it's shifted towards the red. Do you see the pattern is the same, but everything's shifted towards the red? Here it's not shifted at all. And then here is the one where it's shifted towards the blue. So star C must be moving towards us. And if I measure how much it's shifted, so from here, just following this line down to here, that distance that it's shifted, I can figure out the speed of the star. So now, which one's moving away from us? Pause the video, work it out. Okay, well, you probably could figure this out from process of elimination, but let's do it step by step. So I want it to, here's the pattern, I want it to be shifted towards the red. Well, this one is shifted towards the red, so star A must be moving away from us. Which star is not moving? Pause the video, see if you can figure that out. Oh, I got you. It was a trick question. Maybe I didn't, but hopefully not. Remember that just because I don't see a Doppler shift, that does not mean that it's not moving. This star actually probably is moving. It just happens to be moving directly across our field of view. It's right in front of us and moving across. So this is like that car that's passing us. So just because I don't see a Doppler shift does not mean it's not moving. It just means I can't tell. It's not moving towards or away from me. It might be moving directly across. All right, so when we're trying to figure out the Doppler shift, the first thing we have to do is we have to identify the substance. And so look on the back page of your class notes then. We've got this substance here. Now take your composition on the back of your practice sheet. You should have your spectral library. We're going to need this. Pause the video, figure out what this substance is. Did you figure it out? It is hydrogen, same one that we did with the last time. So hydrogen makes up 99% of the universe is hydrogen and helium. So anytime you're not sure what something is, hydrogen and helium is a pretty good guess. But in this case, I want you to compare the lines here. All right, so this is hydrogen. That's our unknown substance. So now the next thing we want to do is we want to observe the wavelength. So this is the rest spectrum, or I'm sorry, this is the shifted spectrum. And you see that this doesn't match the exact numbers from the rest wavelength. Well, that tells me that this thing's moving. So the observed wavelength, and we tell you each tick mark is 5. So I'm going to count how many tick marks. It's 1, 2, 3, 4, plus a little, right? So that's going to be 5, 10, 15, 20. So that would be 670 plus a little. So let's call it 673 nanometers. As long as you're, don't say it's 670, don't say it's 675. As long as you're somewhere in between there, you're fine. All right, so the observed wavelength was 673. Now you always want to use the reddest line. The reason for that is it will have shows the most shift. So it will find your job a whole lot easier if you use that reddest line. All right, now when you look at the original spectrum, look on your spectral chart here, not on the screen, but on your spectral chart. What's the rest wavelength of that line? Well, when we look at that with hydrogen, it's going to be, looks to me like it's a little bit more than 1 mark. So that would be 650, 655, and then plus a little bit. So you might say it was 657. In reality, it's 656. If you use 657, you're going to be close enough. It's going to be fine. But 656 nanometers is the actual wavelength. So it really shows up right here on your chart, but then it shifted this much. So let's do the math. Let's figure it out. So first thing you want to do is you want to put in your observed wavelength, 673. Put in your rest wavelength here, 656, and my rest wavelength here is going to be 656. And I'm using 3 times 10 to the 8th because I want my answer in meters per second. I'd do 3 times 10 to the 5 if I wanted kilometers per second. You never have to memorize constants, just be careful with the units. All right, so pause the video, put this in your calculator, and let's figure it out. Okay, you should be getting 7.78 times 10 to the 6th, e to the 6th, meters per second. So if you're not getting that, go back, see if you can figure it out. First thing to remember is that you always want to either put in these parentheses, or what I like to do is do 676 minus 656, 673 minus 656, and hit equals, and then do divide by 656, and then times 3 times 10 to the 8th. Either way works. Just make sure that you're keeping this part separate from the rest of it. So double check your work, make sure you're getting 7.78 times 10 to the 6 meters per second. Now a little bit shorter way is that we could just find the shift. Well, we said that it was 673 was where I observed it. Instead of, let me go back to my spectrum here. Instead of actually doing the math, I could sit here and say, okay, well I started here and then count how many tick marks over you went. And so if I start here, that's going to be 1, 2, little over 3. And so that's going to work out to be, call it 17, just because I happen to know what the numbers are. Again, if you're close, you're going to be fine. So you can just figure out the shift, and that's fine. That works really well in Smart Sparrow. So this then is going to be our shift, but 17 divided by 656 times 3 times 10 to the 8th gives me exactly the same answer. All right, so we mentioned that our speed of light is 3 with 8 zeros, 3 times 10 to the 8th if it's in meters per second, but it's 3 with 5 zeros if it's in kilometers per second. Think about that. A kilometer is a lot further than a meter. It's 1,000 times further than a meter, so I'm not going to be able to go through as many of them in 1 second as I can here. Either way, just look up which one you want. It might be a good idea to actually write that down on your reference sheet. So if I've got 3 times 10 to the 8th meters per second, or 3 times 10 to the 5th kilometers per second. Always, always, always when you're doing Smart Sparrow, look at those units because that's going to tell you which of these constants you should use. Okay, so remember it's the shift in the wavelength. So what I find a lot of students will do is they'll do, like our example we had before, they would do 673 divided by 656, and that's not going to work. It's going to give you a number that's greater, your velocity is going to be greater than the speed of light. If that fraction comes out to be bigger than 1, you've done something wrong, figured out what it is. But most of the time, they're putting in the observed wavelength instead of the shift in the wavelength. So remember that fraction should always be a very, very small number from that. If you remember that, that'll usually help you out. So as always, I'm here for live help. If you've got any questions, just pop in. Glad to talk to you and get you going. We'll see you next time.